All right, we started section 9.2 last time, multistage experiments, and we looked at some experiments where we were putting like names into a hat or something like that, and we were drawing them out, and so each of those draws affected the next draw. Those were events that were not independent events, and we talked about events that were independent events as well, where one outcome does not affect the other, and so, for example, a lot of our games have that play. So. When I draw or when I roll a dice, the next roll, the second roll, has absolutely no bearing on what the first roll was, right? It doesn't make any difference. But there are some card games too, card games specifically, that do, right? Like if I draw a number out of a deck and I keep it, then the next draw will be affected by what I drew the first time, right? It changes those probabilities as we go. So we had done some examples where they changed and some where they did not change. So we're going to do a few more examples that are more application-based in nature and less game-based in nature. So here's one. So I created this problem a long time ago. It might still be true. So when I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears the shirt. If the shirt is stained, there is a 0.2 probability that I will not be able to adequately remove the stain. What is the probability that my son's new shirt will be permanently stained the first time he wears it? So I do this example because I want you to see that not all tree diagrams are balanced. So this was the tree diagram we did last time, where every time I drew a set of branches, there's another set that sort of balanced out what came off of it. It doesn't have to work that way. And so this is an example of one that doesn't. So the first scenario, or the first piece event in my scenario here, is that my son wears the shirt, and what happens? What are the two outcomes that could happen when he wears the shirt? He stains it or he doesn't, right? So these are my first two set of tree branches. The first one is that he stains the shirt, and the second one is that he doesn't stain it. So I'll just say no stain. Okay, so what's the likelihood that when he wears it, the shirt gets stained? What's it say? 0.15. So what is the probability that he wears the shirt and he doesn't stain it? Point what? 8.5. Yeah. How did you get 0.85?
1 minus.
Yeah. So remember, every set of tree branches have to add up to 1. Okay, so you can get the other piece when there's two branches simply by subtracting. Good deal. Now, this is a scenario where I don't need to draw branches over here. I don't have to do it quite like that. In particular, I don't need branches on the no stain one. Why? I don't have to remove it if there's no stain, right? So the second set of branches only come off the stained shirt category. All right, so after the shirt's stained, it's going to get laundered. If there's no stain, there's nothing to do. But if there's a stain, then I have to scrub the shirt, right? So I've got to try and remove the stain. And I might be able to be successful and do it, or it might be permanently stained. Or you could say it's not removable or something like that. So the descriptors that you use, they should be adequate, but they don't have to be exactly the same as mine, right? They need to mean something similar. All right, so what's the likelihood that if I scrub the stain that I am able to adequately remove it? 0.2 is actually yeah, so 0.2 is that it's permanently stained, and then 0.8 would be that I'm able to adequately remove it. It's clean when it's done. Okay, so our tree branches don't have to be perfectly symmetric when they're in the drawing, and they don't have to have the same value along each branch. It depends on the scenario of what's being described. So the question that is being asked, though, is, after my son wears his shirt, what is the probability that it's permanently stained the first time? So it means I need to end right here, right? And how did I get there? Well, I had to stain the shirt, and then I had to try and get it out, and it didn't work. So how do I find the probability along a single branch? Nope. Multiply it. Yeah, so along any kind of branch that I'm wanting to know the outcome, I multiply along the branches. So I would take 0.15 times 0.2, and what would I get? It is 0.03. And if you're thinking about that in terms of percentages, that's a 3% chance. That's what that would look like. And it's got to be higher than that in real life. These are totally made up numbers. You get that, right? Just made up the numbers right there. Yeah. All right, there's at least one problem can I think off the top of my head where you're going to have this sort of an unbalanced tree diagram going on within either the homework or the group work, okay? So just be aware of the fact that that is a possibility. All right, let's take another one. Joe. Joe says that if a family has 2 children, their only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? So what we're going to do is we're going to draw what a tree diagram would look like for having 2 children. Okay? So, I have 2 children. Child is born, and I have 2 choices, right? It's a boy or it's a girl. And what is the likelihood of each of those things happening? It's 50-50. So you can choose, do you want to use decimals or do you want to use fractions? What do you guys want to use? Decimals. All right, decimals it is. We'll use decimals on this one. And I have 0.5 and 0.5. Okay, everybody good? Okay, this is child number 1. These are my possible outcomes. So this branch represents one, pregnancy essentially. And then I need to do another set of branches to represent that I'm having child number 2. So, looks like that. So again, on each set of branches, in order to get child number 2, I would have a boy-girl option. And along each branch, the probabilities would be 0.5, right? So this is not like the last problem. It's not like the first problem even where I'm putting the names in the bucket, right? Each event is independent of the event before, and each event is equally likely. So I have 0.5s on everything. But again, notice, right, they always add up to the value 1 along any pair of branches. Okay, so along the top branch, the outcome is boy, boy. Along the second branch, the outcome is boy, girl. Along the third branch, it is girl, boy. And along the fourth branch, it is girl, girl. So one statement that you could make is there's really not 3 outcomes. There are 4 outcomes, right? Because we would consider sort of the order of birth affecting things being different. So we could say that to Joe. That'd be one option of something to say to Joe to sort of be aware of. A different option is you could say, yes, there are 3 outcomes, 2 boys, 2 girls, or 1 of each. But what do you notice if I find the probabilities along each branch? What's the probability of having boy, boy? One what? How do I find a probability along branch? Multiply. So what, I've written it as a fraction. We were using decimals. What is it if I multiply 0.5 and 0.5? 0.25. The second one is also 0.25, right? And the third one is 0.25. And the fourth one is 0.25. So what's the probability of having 2 boys? Well, it's 0.25 or 1/4, not 1/3. And the reason that happens is because there are 2 distinctly different ways I could have ended up with a boy and a girl combination of children, right? So if you want to know the probability of having a boy and a girl, it's not 1 out of 3. What happens when I add 0.25 and 0.25 together? Yeah, it's 0.5. So I have a 0.5 probability of having 1 of each if I've got 2 children. It's a 50-50 shot. 50-50 shot says I have 2 children of the same sex or I have 2 children of differing sexes. That's what this is actually showing. So there's several ways that we could sort of respond to Joe. This tree diagram gives us a good idea of how to think about it. And so let's write down a little bit of what we could say first of all, he's not quite right. Not Joy. How about Joe? Joe is, we'll say what he is correct about too. Correct that there are 3 outcomes. But the outcomes are not equally likely.
Is that because you can have the probability of having a boy and a girl is 0.5? Is that why they're not equally likely?
Yes. So there's a 0.25 probability of boy-girl and a 0.25 probability of girl-boy. So it's a 0.5 probability of one of each. Right, that's the unequally likely part, if I think about there really being 3 different sort of outcomes to what's going on. Now, this isn't the only way I could write this. I could simply say he's incorrect. There's really 4 outcomes, because the outcome of boy-girl and the outcome of girl-boy, because of the ordering, is a different outcome. So therefore, there are 4 equally likely outcomes, not 3 equally likely outcomes. So I could approach it from that perspective, and it would be equally correct to say so. And I do need to say that the probability of 2 boys, because that's actually the one he's talking about, is actually 1/4 or 0.25 in order to fully answer that. Somewhere in there I've got to describe that that's what's happening with my boy-boy combination, since that's the ones he referenced. Does that make sense? So depending on your perspective will depend on how you write it up, but both would be equally likely, or not equally likely, but equally correct statements to say. All right. You ready for a real-life example? So the next one is that. Okay. Are you familiar with Huntington's disease? Okay. Huntington's disease runs in my family. It is a degenerative disease. It affects your central nervous system. Basically, it makes all of the things that we take for granted of being able to do very quickly slow down. So the time it takes your brain to tell your hand to go up when you want it to go up is slower than normal. My grandmother had Huntington's disease, and so did my father. And in 2001, which is, not much before you guys were born at this point, 2001, right? 2001, my parents decided that they were going to tell us that this is what my grandmother had and that my dad had it. We didn't know my dad had it at that point. The children of us, my family at least, didn't. The probability that a child has Huntington's disease, if your parent has it, is a 0.5 probability. It's very much like our boy-girl diagram here. It's all 0.5s. So we knew that my grandma had something. We had no idea what it was really at that point, the children in my family, myself, my brother, my sister. And we did not know that my dad had it. And so it was literally days before Thanksgiving, or maybe it was actually I think it was at Thanksgiving, that my parents decided to share the news with my family. What it does is it causes you to deteriorate faster. So my grandmother passed away when she was in her early 60s. My dad was not that old. He was in his mid-50s, and the last maybe 7 or so years of his life, he was deteriorating to the extent that he couldn't do the things that he loved to do. And I think that's very young to pass away. So the things that I remember that would affect them was I remember going to a Golden Corral where you have the ability to do the self-serve ice cream. You guys know what I'm talking about, right? And I remember my grandma at that point not being able to stop the self-serve ice cream, and there was a big mess of self-serve ice cream. One of the last things that I remember in terms of them taking away her freedom, if you will, was she'd had a number of small accidents because she couldn't stop the car before she hit the car in front of her. her reflex time slowed down. She couldn't do that anymore. I remember her losing her balance, not being able to walk steady on her feet. I remember my father having to sort of like hunch over to try to keep his balance. That's the way. So if you would have asked my son before my father passed away, my son would have told you that my father, he called him Opa, walked around like this, trying to keep his balance. And so it affected, my dad was a very active man, like avid bicycle rider, like bike, and then eventually motorcycle as well. He totaled 2 motorcycles. And that kind of was the end of his ability to ride those kinds of vehicles because he couldn't maintain his balance. He couldn't have the stopping time. All that kind of stuff started slowing down. Eventually, what ends up happening with Huntington's disease is you lose the ability to swallow. That's a problem. And so it's a very horrible disease. And maybe one of the worst parts of it is that the belief is that your mind remains completely intact. And so, like dementia patients, you're like, oh, they're sweet and they're funny. My grandfather had dementia. And because he doesn't really know fully that he doesn't really know fully, right? So you can see from the outside looking in that he's deteriorating, but he doesn't have full comprehension of that fact. And with Huntington's disease, the belief is that you do. You fully know what you can't do anymore, and you have no control over being able to do it. So it's very, very awful. So my parents decided at the time that they were not going to share that news. My dad was actually diagnosed with it in 1995. So 6 years before, would have been when I was in high school. They knew for 6 years before they told us that that's what my father had, and that my grandmother's disease was that as well. And so they told us, by the way, so your dad has it, and there's my brother, my sister, and I. There's 3 of us, and each of you has a 50-50 shot of having it. At the time, I was married. I'd been married for 3 years almost. My sister was married and had been married for almost 1 year. And my brother was seriously dating the woman that he ended up marrying a few years after that. And so all of us were in fairly, long-term, at least presumably at that point, relationships. And my parents decided they were going to tell us. And the reason that they told us about this was because it would affect or could affect our decision on how we would structure our families moving forward. And so that night, I literally we're going to draw a tree diagram for it, but I did the mathematics behind the tree diagram, sort of processing through what this meant for my life and my family moving forward. So I'm the oldest of my parents' children, and so this branch is actually me. And there are 2 possibilities. There's a possibility that I have Huntington's, and there's a possibility that I don't. And we did the last one with decimals, so let's do this one with fractions just to see a version of it that's slightly different. It's 1/2. It's a 1/2 probability that because my father has it, that I will also have Huntington's disease. My sister is child number 2. So this set of branches is my sister. And she has all the same possibilities, right? She either has it or she doesn't. So have or don't. Have or don't have. And once again, the probabilities along each branch are 1/2. If you want to write them in decimals, you certainly can. And then my brother is the next. He's the youngest. So these last set of branches are him. And I'll abbreviate with H's and D's at this point, which interestingly enough is my abbreviation for Huntington's disease above, but he either has it or he doesn't. And each probability is another 1/2. Kind of running out of space to put these on here as a cut paste option. Okay, they're all there. You can barely see them all. And so what I did in my mind that night is I was trying to figure out what's the likelihood that none of us has it. Because I watched my grandmother and I watched my father go through this, and it's awful. It's really awful. And so the first question that we're, oh my goodness, I understood. The first question that we're asking ourselves right here on part A was the reverse of that question. Not what's the likelihood that this is going to escape us all, but what's the likelihood that at least one of us is going to have to deal with this in the future. And if you take a look along all of the branches, there's only one branch where we're all free and clear. That branch is the very bottom one where it says don't, don't, don't. And so this branch right here, whoops, highlighter's what I meant, is the one that I was doing in my head that night. And it's a 1/2 along each one of those branches. So the probability that we're all okay is 1/2 times 1/2 times 1/2. And that's 1/8. Which means the probability that someone is affected is 1 minus that. And 1 minus 1/8 in fraction form would be 7/8. Can somebody tell me what the decimal is for that? Do you have it, Laura?
7.5.
Yep. 0.875. That's really high. It's really high that one of us is going to have this disease. And like I said, I was married at the time. I mean, I'm married still, but I mean, like I was already married at that point. I had been married for 3 years. We didn't have any children yet. And my husband and I were really just processing through these numbers, because numbers is where my head goes, because that's what I do for a living. And I knew that if I had children and I didn't know what my status was, that I was pushing forward this decision to my children's stage one more, right? I was putting my children in the same position that I was currently in myself. And so that night, right then that night, my husband and I said, if I have this disease, I'm not having kids. And that was not a popular decision among our family members. They were very not okay with that. And the reason they were very not okay with that was my mom felt like if she had made that decision, you know, like I was making that decision looking forward, that none of us would be here. My sister, my brother, and I wouldn't be alive. And she wasn't okay with that as a forward-moving thing. And I felt like looking backwards different than looking forward. Looking backward and saying, but if I had made that decision in the past, X, Y, Z wouldn't have happened is different than saying, but moving forward, like it makes it a different choice. And so that is the decision that my husband and I made. And so we had been married for 3 years, but we were still very young. We got married very young. And so we weren't quite at the point where we were ready to have children yet anyway. And so there is a genetic testing process by which you can actually be tested for Huntington's disease. Huntington's disease being a geometric's not the word I want. Genetic disease actually means that they count like triplet repeats on your chromosomes. Like it's a very involved test. You have to get psychological counseling before you get the test taken because they want to make sure that you're going to be able to handle the results, that you're going to be okay with what the answer is. When we went through psychological testing for it, they literally looked me in the face and says, what if this decision means that your husband leaves you? I said, well, he's not going to do that. And they're like, well, how do you know that? I said, well, I know that because of our faith in the Lord. So we had to go through all this testing to, like all this psychological testing to even get the genetic test done. And so what happened is that 2 years later, actually, so in 2003, I was tested for Huntington's disease and I don't have it. But during that 2 years, God made it really clear to my husband and I that while we were going to get tested for Huntington's disease, and if we had it, we weren't having children, that no matter what that test came out as, that adoption was going to be part of the story he was writing for our life. So I was tested. I don't have Huntington's disease. And because I don't have Huntington's disease, I have one of my daughters. Abigail is the one that you've seen pictures of before, and she's my one biological child. But because of that 2-year time frame, and because of this instance in our lives, God really made it very, very clear to us that adoption was going to be part of it. Whether it was the only part of it or just part of it, we knew it was going to be what's going to happen. And as a result of those things happening, I have 7 adopted children, or I will be once adoption's finalized for the last 2, right? And so I think it's very interesting that that God uses those things that are just truly tragic things, because I will tell you that Huntington's disease is awful. But I also believe that if you were to ask my father and my grandmother in heaven, has it brought something about that's beautiful? I think it has. My siblings have not been tested. My sister has 3 children. My brother has 2 children. So all of them are in the category of what they would consider to be at risk for Huntington's disease because they have never been tested. You can't get children tested. You can only test somebody who's 18 and up, and that's it's a law, I guess. I don't really know how that all works, but you can't be tested if you're under 18. So the third question, or the second question on this right here, asks, what about my siblings still? So I don't have Huntington's disease, and what that means in terms of this diagram that I drew over here is that everything on the top half doesn't exist because I don't have it. And while you could still do this bottom part of the diagram, this 1 point, this 1/2 wouldn't exist anymore. It'd be a 1. Because I've been tested, there is a 100% chance that I do not have it based on that genetic testing. And there's a 0% chance that I do. Which means this diagram collapses, and there's not even this part of it on here because it's a 100% chance, right? A 1 probability. So this is the diagram that still remains. So over here is what we still have. We'll see if I can copy it to the next page. I will probably have to delete part of it because the pink is still there. This is the diagram that remains. And I can do the same thing that I did with the first diagram. I can look at the likelihood that at least one of my siblings has the disease. And I can calculate it the same way. This right here is the everybody's okay kind of scenario. So there's still a 1/2 probability that my sister has it and a 1/2 probability that my brother has it. And we could continue the diagrams after them, right? Because they have more children, each one of them. So there is a 1/4 probability that they're both okay. So this is the probability that they're both okay. So the probability that still someone has it is what? Mm-hmm. 1 minus the 1/4, or 3/4, which is probably a decimal that you're very familiar with, is 0.75. So there's still a 0.75 probability that my family is still affected by this disease.